welcome to our group 5 and going to present the optical switching from Material Science Department of National Singapore University. First, I'm going to do the introduction of the M&M devices and the optical switching. The basic principle of the M&M device is having a two magnetic layer with this one tunnel layer, and when we introduce the current, the magnetization direction of the two layer, pinate layer and the free layer are in the same direction, then they are having the low resistance, and when they are opposite they have the high resistance. So this phenomena we are using to store the data in the M&M devices. There are different type of the phenomena used to switching the devices. So one is the spin orbital talk. So in this spin orbital talk and devices, we have the two type of the channel. One is for the reading and one is for the writing. In SOTM, we have the same structure with the one heavy metal layer in bottom. So when we introduce the current inside the material, and there is different type of the induction take place, which with the effect of the Rushwa and spin Hall effect, and we generate the different type of the damping like the torque or field like torque to change the magnetic direction of the materials. It's a basic and generally using SOT devices and AMRAM, but there are some advantages and disadvantages with these devices, like fast switching speed and low power consumption. But the disadvantage is that they have the complex fabrication and the high current density required for the writing. The other one is the spin transfer torque. So in these devices we have the single path for the reading and writing. That is the problem in this device, because for the having the single path of the reading and writing, there is the reading disturbance a lot, and the breakdown of the tunnel junction can be occur if we have introduced the high current, and this high current reading and writing high current can be slow down the speed of this system. So for the SOT material, we don't have this problem because we have the two channel, and this is the one channel devices. So most of the time people are prefer to the SOT devices, but it's depend on the type of the application you want to use. So the best way the researcher found is the optical switching is different from the SOT and STT switching devices, because it's a non-contact switching. Switching in field, we introduce the field, external magnetic field, and it creates the strain to change the magnetization direction. In the current like SOT or STT switching, we introduce the current and heat is generated and the switching is take place. But in the optical switching, we introduce the light or the laser pulses, which can generate the heat or change the direction of the magnetization, and you can control the reading and writing process. And the phenomenon behind the optical switching is the inverse Faraday effect or photomagnetic effect or ultra demagnetization. This effect can be there. As you can see in this device, we have the gadolinium, cobalt and platinum structure, and they introduce the probe laser on the top of the devices. So the effect is take place is the heat transfer laser, and the laser can transfer the heat to the system, lattice and the spin of the material, and the magnetic circular dichroism take place because it's a circular polarized light. So they have the different handedness. So the handedness is the as equal as the magnetization direction, then we can transfer the more energy to the system, and the effective magnetic field will take place to change the direction of the magnetization. And the cause of the producing of the effective magnetic field generation is the exchange interaction between the nearest spin of the lattice and the DMI of that spins, and the spin orbit interaction also possible to generate the effective magnetic field to switch the direction of the magnetization. So here is an example of the gadolinium iron cobalt structure, and they introduce the laser on this device, and you can see the different type of the handedness of the light, and that they'll introduce the laser at the different time with the pulse width, and you can see in the first shot that they are magnetized, in second shot the magnetization is just disappear. So they magnetize and demagnetize the material as they introduce the pulse, and the Hall voltage also change the condition, and there is the toggle switching take place in this material, in this structure. So what material we can use? So the most specialized material we use here is the rare earth material and the transition metal combined alloy. So we can use the gadolinium or terbium palladium, or in transition metal we can use iron, cobalt and platinum. The structure we have to consider is the heterostructure or the multi-layer. They are now known to for the optical switching. There are many advantages with the optical switching, like low crosstalk, low power consumption, but there are also some challenges like integration challenges. It's very difficult to integrate with the CMOS devices. Scalability is also a problem because in nanoscale MN cells we are going to work, and the high intense laser using to increase the thermal effect, which one the devices or change the condition of the material, and due to using the equipment and material requirement for optical switching are very expensive, so the cost is a concern way to the research to lower down it. So in next slide we are going to show a different material how we can do the a different type of the optical switching, and then we can work with these challenges. And my big thanks to all for their time.
I am He Chenyuan. After the introduction, I'm going to talk about some early studies of photoferrics and photoferrites recording. And the term photomagnetism is first mentioned at 1964. And silicon-doped ethereal iron garnet, YIG, is one of the most popular compounds in these studies. Why? Because YIG is a material that have a significant change on magnetic and isotropic, and after the illumination. This is the picture of YIG, and this is its crystal structure. The gray one is the Ethereum, and the red part is the iron, and the white one is the oxygen. Before we talk about what's changed after the illumination, I want to talk about MR, magnetic resonance first. So what is MR? In every magnetized materials, there will be some certain magnetization directions. After we applied an external field large enough, these direction may start to precessions like this, just like the graph indicates. And this behavior was described as magnetic resonance. So this leading to what? Because MR values is said to be in part related to magnetic materials and isotropic. So if a magnetic materials responsive in MR, for example, the value of applied magnetic field changes, it also indicates the change in anisotropic. So which leads to this graph. After the light is switched on, we can see the applied field to cause the magnetic resonance in YIG has significantly decreased compared to the unilluminated curve A. So what kind of light it is? It is an unpolarized near infrared light. So the applied field changes indicates the change of the magnetic anisotropic of the YIG. So this is the point that the research want to talk about. In a similar case is a gallium-doped spinel codium chlorurium cellulium. So in the spinel, there are tetrahedral sites and octahedral sites. And the doped gallium will substitute into these two sites. Why I talk about this is because usually the magnetic property chains are originated from the substitution behavior of the impurity atoms in the crystal structures. So for this graph, instead of changing the anisotropic, the permeability of spinel rapidly dropped on a time scale of seconds after the light is switched on. And under 77 kelvins, it is reversible, and usually you can recover to very close to its original value. But however, under 42 degrees Kelvin, it has an irreversible effect. So these are the two cases of early studies about the interaction between photon and the change of magnetic properties. And the last one to talk about is the photomagnetism recording. They used the ethereal iron garnet and doped it with a silicon. So what's special about it is instead of using an unpolarized light, we used polarized light. And the parts illuminated by the polarized light, its magnetization direction will reorientation with a smallest angle between the magnetization and the polarization of light. So therefore it creates a difference between the illuminated part and the unilluminated part. So which can be shared as a method to store an information on YIG. So you can see from this graph, by using curve microscope, 3 letters K, R, Y are stored on this film because polarized light creates a different magnetization directions compared to the other unilluminated part. So this is basically the first research about the photophoretic recording. And this is all my part. And the next part will be theory. Thank you.
Next, I'll be discussing the two mechanisms of all optical switching. So the contents in this part are mainly from the research paper here are listed at the bottom left corner of the slides for your reference. So here I illustrate the experiment setting of the research. So you can see here we have a 5 micrometer wide hot cross and a certain size of laser beam is shined at approximately 40 micrometer away from the cross center along the x-axis, and our all optical switching is obtained just right in the cross center area. So the two mechanisms are single pulse switching mechanism and two regime switching mechanism. So let's take a look into the single pulse switching mechanism first. So this mechanism is observed in gadolinium iron cobalt system, which is a kind of ferromagnet. What you should know is that the gadolinium sublattices and the iron cobalt sublattices in this material exhibits a antiferromagnetic coupling at the ground state. So when you shine a single pulse of laser beam on the material, it actually provides a thermal energy for the spin in iron cobalt sublattices and spins in the gadolinium sublattices to flip at different rates. And this unique properties allows the transient alignment of moment to occur each time we shine a laser beam on it. And note that this process can induced only by heat and is helicity independent, which means the polarization of light doesn't matter as long as we have a high fluence of it. And next we have two regime switching mechanism, which is observed mainly in ferromagnets like platinum cobalt system and the terbium cobalt system. So just like its name, the two regime switching mechanism composed of two steps to achieve its switching, which are a helicity independent multiple domain formation followed by a helicity dependent remagnetization. So let's take a look at step 1, helicity independent multiple domain formation first. This step is a demagnetizing process. So in this step, heat is also involved, but this time the heat does not flip the spin directly, but instead it provides a energy for new magnetic domains to form and randomizes the initial magnetization. So when you measure the whole voltage, it exhibits a step-like drop behavior on the figure. And notice that the time scale for this effect is within 1 millisecond. And after the helicity-independent demagnetization, we certainly have helicity-dependent remagnetization. So the domain wall motion in this remagnetization process can be explained by two effects, which are magnetic circular dichroism, which causes different absorption of the two helicities in different domains, and stimulate spin current via spin Seebeck effect. And the other is inverse Faraday effect, which also explains the helicity-dependent remagnetization. What's interesting is that other than inverse Faraday effect mentioned by other research group, this research also found that for the all optical switching to occur in cobalt platinum, the remagnetization process requires not necessarily a paramagnetic state, but a multiple domain formation is certainly needed. So the timescale for this effect can extend to as long as tens of milliseconds. So as a conclusion, we have single pulse mechanism and two region mechanism for different kinds of materials to have all optical switching. So in single pulse mechanism, we know we can observe this mechanism in gadolinium iron cobalt ferromagnets, and it's a helicity dependent process and due to different spin flipping rate of different sublattices. And next we have two region mechanism, which we can observe it in the platinum cobalt and the terbium cobalt ferromagnets, and it is actually a cumulative effect, and it composed of a helicity independent demagnetization and a helicity dependent remagnetization.
Hello, I'm Aryan and I'm going to talk a little bit on the various device level advancements that have been made with optical switching in recent times. This paper from 2017 was the first one to demonstrate ultra-fast all-optical switching of an MTJ using sub-picosecond infrared laser pulses. They use ferrimagnetic gadolinium iron cobalt as a free layer, as you can see in the figure A. The tantalum and palladium layers are used as the buffer and the bottom electrodes. The cobalt palladium multi-layers as the fixed layer, which is optimized to obtain good perpendicular magnetic anisotropy. Notably, ITO is used as a transparent top electrode to allow optical access. The TMR of the MTJ is measured by sweeping a perpendicular magnetic field in the range of 2 kilo-oersted, as you can see from figure E. The TMR ratio was observed to be around 0.6%, which they attributed to the quality of the MGO layer, which had not been annealed. Finally, the figure F shows the optical switching measurements, where each 0.4 picosecond pulse is responsible for switching the MTJ between high and low resistance states. Here also the TMR ratio was 0.6%. Another much more recent paper used gadolinium cobalt bilayer. In this configuration, the TA makes up the bottom electrode, and the combination of the cobalt platinum Mn multi-layers with the bottom cobalt iron boron layer serves as the synthetic antiferromagnetic reference layer. Such a design is used to fix the magnetization direction of the bottom COFEB layer, and here also ITO has been used as a transparent top electrode to allow optical access. The composite FL layer, which is made up of COFEB MGO bilayers, it has been coupled with the optically switchable cobalt gadolinium bilayer through a 0.3 nanometer thick tantalum spacer using RKKY interaction. Such a design satisfies relatively high TMR ratio of 34.7%. It also offers higher PMA and an ultra fast AOS at the same time, because it only takes like 10 picoseconds for switching to happen. And also the energy consumption is much more less compared to the previous MTJ. In another paper that came out in 2019, they attempted to integrate optical switching with domain wall racetrack memory. Measurements were performed on tantalum, platinum, cobalt, gadolinium, platinum stacks which were deposited on silicon substrate. The samples were patterned into 5 micrometer wide wires, with each wire containing two sets of lateral legs. The AHE signal in the Hall crosses is measured using lock-in amplifiers Li1 and Li2. The red dotted circle, which is shown on the figure A, illustrates the region exposed by the laser pulse, and figure B, which is the bottom figure, shows the normalized AHE signal of the two Hall crosses as a function of time. The red dotted lines mark the beginning when the writing is done by AOS, and the bottommost plot tells you the arrival of that domain wall after being driven by SHE through SHE uh, through the length of the wire. There is a little bit of an offset, which you can see shows the traveling domain walls through the wires, and it's also shown here in the mock image. There So this plot shows the comparison between other switching schemes. The 68, this one was the first MTJ that was produced that I talked about, and this, as you can see, offers much smaller switching time compared to these other MTJs, which are based on STT, SOT, and electric field controlled mechanisms. This new hexagon shaped data point refers to the optospintronic tunnel junction that we just talked about. Not only does it offers much less switching time, it also has a less switching energy compared to its predecessor that came out in 2017. So as you can see, it is much better whether you talk about the switching time or even the switching energy compared to the other MTJs. There are a number of limitations that OTJs have compared to MTJ. The low TMR ratio is definitely an issue. The high optical pulse energy that femtosecond laser have because of their much larger laser diameter compared to the size of the device that they operate on results in energy wastage, which has to be addressed. Also, scalability is a huge issue because femtosecond laser are huge equipments, and they need to be miniaturized before we can think about using MTJ in our everyday electronic items. That's it for me. Thank you.
In the following, I'm going to introduce the challenge and solutions for optical switching by femtosecond laser. 1. Heat management. The challenge. High energy pulse laser often lead to excessive heat generation, disrupts the magnetic order, causing demagnetization of domains and hindering controlled switching. The solutions. 1. Laser parameter optimization. To optimize laser fluence such as wavelengths, pulse shape, and pulse duration for specific materials, and minimize energy dissipation and precisely controlled heating. Next is advanced substrate materials. Utilizing substrate with high thermal conductivity to efficiently dissipate heat away from the medium. The third one is active cooling system, implementing dynamic cooling mechanism during laser irradiation to manage temperature precisely. 2. Speed and control of magnetization reversal. The challenge, the sub-picosecond switching bottleneck. A conventional method relied on precessional switching, which takes at least 2 picoseconds. The second one is insufficient angular momentum transfer from the light due to limited photon availability in practical laser parts. And the solutions: advanced laser systems, laser capable of generating even shorter or more intense pulse with precise control over pulse shape and duration. Enhanced photon efficiency, multi-photon absorptions or nonlinear optical effects utilize high-intensity laser and materials with strong nonlinear response. Alternative light source with high harmonic generation to produce higher photon flux. In the following, I'm going to introduce the future research direction. 1. Advance the laser system and techniques. Enhancing the precision and control of femtosecond laser system. This includes developing lasers with tunable parameters and higher stability, as well as novel techniques for more efficient energy delivery and reduced heat generation during optical switching. The second, heat management and energy dissipation. Effective thermal management strategy must be developed to handle the heat generation during optical switching. Research should focus on reducing energy dissipation, improving heat sinks, and employing advanced cooling techniques to maintain the efficiency and the stability of magnetic memory device. 3. Material optimization and innovations. The materials should possess the following properties: superior magneto-optical properties, high magnetic anisotropic, and thermal stability. Some examples are given as follows. The first one, iron platinum. Stable magnetic orientation at nanoscale dimensions. Withstand high-frequency optical excitation without significant degradations. Suitable for efficient optical magnetic switching. The second one is a gadolinium iron cobalt and a terbium iron cobalt. Strong magneto-optical effects. Suitable for ultra-fast optical switching. Tunable magnetic properties enable precise and efficient optical control of magnetization. The third one is dysprosium ions. Ensures stable magnetic orientation under intense optical excitation. Suitable for high-frequency optical magnetic switching.